Alright, welcome to Chapter 8, Systems of Equations. This is more of a continuation from your previous math course. Probably went over systems of linear equations, and what this is going to piggyback on is that chapter, and we're going to talk about systems of equations that involve quadratic functions as well as linear functions. Okay, the first section we're going to talk about solving systems graphically. So you're going to need some kind of graphing technology. I'm going to use an online graphing calculator called Desmos. Okay, Desmos online graphing calculator. And this is a really good calculator. It's free, and you can have an account and save all your functions, save your work, so you can label this section, if you make an account, as section 8.1, return to it later, and add to it and play around with the graph, so it can be kind of useful. Or you can use any kind of graphing calculator that you might already have. So before basically the how this chapter is going to be arranged, well, we're going to start by graphing things, or by solving things graphically, solving through graphing. And solutions will look like intersections. Okay, points of intersection. This is a good way to start, because while you don't have to worry about the algebra, you're going to be able to understand what's happening. Okay, so here's a nice visual representation of what's happening. Then we're going to move on and solve things algebraically. Okay, that will be 8.2. 8.1 is what we'll do today. Okay, so what's the point of doing this? Well, systems of equations, and what that means, systems of equations will be more than one equation that you're going to solve simultaneously. Okay, so for instance, a system of linear equations would be something like x plus 2y equals 4. Okay, and the same system has 3x minus 4y equals 7. Okay, what is x and y? And we can solve this using a few basic procedures known as elimination and substitution, but we'll worry about that in 8.2. We'll get into the techniques of how to solve this algebraically later on. You could also solve this by simply graphing both of these, and their intersection will show you the points, will show you the solutions. Okay, and sometimes you can use these graphs to model certain situations. Okay, so we're going to talk about linear quadratic systems and quadratic to quadratic systems, and then we'll solve some problems. So let's take a look. There are multiple results that can occur when solving these equations. So you can have no real solutions, you can have one real solution, you can have two real solutions, and you can also have infinite number of solutions. Okay, I'll show you what these look like. So here's an example of a linear quadratic system, right? Because you have one linear, one line, and you have one quadratic. In this system, there's no intersection, no point of intersection. Therefore, there's no solution. Okay. This next one, you can see there's only one point of intersection, therefore one solution. 2 points, two solutions. So those are your three options. Here's quadratic equations, right? These are both quadratics. Again, no solution, one solution, two solutions. What's an infinite number of solutions look like? Well, this will only occur if both graphs are on top of each other. So if say you have one quadratic equation like this, and then you have another one, we'll do in blue, that would be perfectly on top. Okay, then every single point is the point of intersection. Okay, we're not going to discuss linear quadratic equations. Okay, so for our purposes, there's only one type of infinite solutions that would be in quadratic equations. So we're only going to talk about linear quadratic and quadratic. We're not talking about, okay, not talking about linear systems. That was the gist of Math 10. So, we already talked about Desmos. Let's do an example. Okay, so I walked you through an example. You can take a look at the solutions. These are all, by the way, graphed using a TI-83 Plus Texas Instrument graphing calculator. But, I mean, they're $100. So, if you don't have one, don't worry about it. We'll use Desmos. So, very simple. Solve the system graphically and verify your solution. Those are the two lines. You can identify this as a linear quadratic system. Right? And let's graph this. So, if I pull up Desmos and I shrink the screen, so you should be able to see that. Our first graph, when we go in here, will be x minus y plus 1. So, here we go. X minus y plus 1 equals 0. And it has a nice graph for us. Then we have x squared minus 6x plus y plus 3 equals 0. Okay, and then we're done. Let's take a look. Let's take a look at what we got here. We'll hide this. So you can see, and this is nice how it's going to let us highlight the points of intersection. So we have 1 and 2 and 4 and 5. So you can see what this graph looks like. You can zoom around. Okay, look at this back. 2 solutions, 1 and 2, 4 and 5. Okay, so we have one and 2, 4 and 5. To check this, to check these solutions, okay, this is a good habit to get into. You're going to plug into both equations. So for 1 and 2, you're going to have the following work. You're going to have, for x, you're going to put in 1s. So you're going to have 1 minus 2 plus 1 equals 0. I'm doing this guy right here right now, which is going to equal negative 1 plus 1 equals 0, 0 equals 0. That checks out to be true. You have to do the same thing for the second equation for the same point. Okay, so you have 1 squared minus 6 times 1 plus 2 plus 3 equals 0. What you're going to get 1 minus 6 plus 5 equals 0, which will come out to be 0 equals 0. So that works out good. Works out well. So now we do the next point. Okay? Let me just move this mic down. Sorry. Next point is, let's see, 4 and 5. So we do the same thing. 4 minus 5 plus 1 equals 0, which will be true. And the next one is 4 squared minus 6 times 4 plus 5 plus 3 equals 0, which comes out to be 16 minus 24 plus 5 plus 3 equals 0, which is 8, 32. Ooh. Let's make sure we did this correctly. 4 squared. And I did do it correctly, so we have 8, 24, that's 0. Perfect. So they're both solutions. So this is your answer. Okay? Now, by the way, since you're graphing it, verifying it is more like, this is just developing skills, because when you see the graph and you can see that they intersect, okay, these have to be the solution. But when you do them algebraically, since you can't see the graph, you're going to want to check some solutions, because some of them might be extraneous, some of them might not satisfy the solution. So the next example will be the same one. This first example, by the way, was talking about linear quadratic, right? And the second one will talk about quadratic. Really, there's no difference since we're doing this graphically. Okay, so you're going to see a graph, and let's go ahead and do it. Okay? So, So I'm going to pull up Desmos once again. We can work in the same graph, but we can just turn it off like this by clicking these two values. And we're going to work with 2x squared plus 16x plus y equals negative 26. And this next one is x squared, plus 8x minus y equals negative 19. Okay, there we go. So you can see we're going to have 2 points of intersection at negative 5 and 4. Okay, I can zoom in here for you. Negative 5 and 4 and negative 3 and 4. Okay, so there we have it. Let me flip my laptop around again here. Move the mic down. So negative 5, I gotta remember these. Negative 5 and 4 and negative 3 and 4. So that's an example of two solutions. So the solutions are negative 5 and 4 and negative 3 and 4. Okay, now we can go through and check them in the same manner as we did before. Okay, and you check them and they're both going to work. Okay, so you can go ahead and I'll leave that to you. Okay, maybe I'll just turn this into an explanation. Check. Okay, and they'll work out. So you can develop that habit. But let's move on. So now let's do an example. So you can read through the example. I'm actually going to read through this example. I give you the solution, quite a detailed solution. But the second question will piggyback on the same question. Suppose that in one stunt, two Cirque du Soleil performers are launched toward each other from two slightly offset seesaws, as shown below here. The first performer is launched, and 1 second later, the second performer is launched in the opposite direction. Each performer is in the air for 2 seconds. The height above the seesaw versus time for each stunt is approximated by a parabola as shown. That one. Determine the system of equations that models the performer's height during the stunt. Okay, and it shows two equations. You're going to be able to get the equation from these graphs. Then you're going to be able to solve the equation, basically solving for this intercept, and interpret the solution. So I outlined how to do this quite explicitly. I graphed it for you. I talked about what it meant. So hopefully that made sense. And hopefully you could complete this next question. If you couldn't, or you want to see how I'm going to do it, then here we go. Same type of question. At a circus performance, the heights above the seesaw versus time of the performance during the stunt are approximated by the parabola shown. Assume again that the second performer starts 1 second after the first performer. Their path is shown on a coordinate grid. So it's really the same question. Different numbers here. I'm going to walk you through how to do this using this graph. Let's use red. So the first thing is determine the system of equations that models the performer's height during the stunt. So basically, I need to get the equations from these graphs. They're parabolas, so we're going to have to focus on the vertex, the vertices. You also have a nice point of intersection here and a point of intersection here, which we'll need. Okay. So first of all, I'm just on this graph, let's just determine what the vertex is. So the vertex for this first one, okay, it appears to be 1 and 4.5. Okay, that's for the first one. For the second one, the vertex appears to be I apologize, it's not 1. It's going to be an awkward number. It's going to be 1.75, right? Because 1's right here, 1.75. So this is 1.75 and 4.5. And this one will be 1.75 and 4.5. Now, let's work with the first one to start here. Okay, let's work with the first one to start. I'm just going to scribble off what these vertices are to the side here. You can't see that, but that way I have some reference. And I'm not sure why I wrote the same vertice twice. Apparently I'm losing my mind. Sorry about that. This is 0.75. Okay, so I'm going to switch slides here. Try to imagine this graph as we move on to the next slide. So first of all, we're going to use vertex form. And since we're in terms of h, right, height, and t, time, I'm going to write this in terms of h and t. So h of t is going to equal a times t minus p all squared plus q. That is vertex form with respect to t and h. Okay. We already know what p and q are. Okay, for the first graph. So here is, I think I did it in teal, which we'll do in blue. First graph. The first graph, let me confirm that. Yep. The vertex was 0.75 and 4.5, which implies that p is equal to 0.75 and q is equal to 4.5. So all we need to do is solve for a, really. And you can do this by picking a point on the graph. To find a. And I'll choose this nice point right here. 0 and 0, perfect point. So I'll pick 0 and 0. Therefore, what we're going to be left with is 0 equals a. Right, I'm plugging everything in. I should have everything known except a. Okay, and I have a little error. Let's just get rid of that. And put in 0. So, now we just have to compute this. It's quite simple. So 0.75 negative 0.5 all squared will be a positive number. So we're going to have 0 equals a times 0.5625 plus 4.5. Okay, so we're going to move that over. We're going to have negative 4.5 divided by 0.5625. So a equals negative 8. Now this is the first graph, so that means we're going to have to be going down, which you are, where the vertex is a maximum here. So the second graph, which I think I did in red, no, blue. Ooh, we'll do it in red. Second graph. The vertex was 1.75 and 4.5. Okay, simply moved over by 1 to the right. Of course, you can do the exact same procedure. Here, p is 1.75 and q is 4.5. So we're going to go along and do the exact same thing. Okay, pick a point in the graph. We'll say the point will be 1 and 0. Okay, this point right here. 1 and 0. That implies we're left with 0 equals a times 1 minus 1.75 squared plus 4.5. Sorry for my writing. It's getting worse as this video goes on, as usual. 1 minus 1.75 squared is the exact same thing as up at the top. As you'd expect. Okay, a will be the same because a actually defines the width of the opening, which should be the same thing. So here a comes out to be negative 8 once again. The only thing that changes is the vertex. Okay, so the 2 points, or the 2 equations, which maybe I'll do in green, are h of t equals negative 8 t minus 0.75 squared plus 4.5. And the other one is h of t. It can't be h of t. We'll make it, let's see. Well, actually, sure. Let's just keep it. Then we have h of t, call that 1, we'll call it 2, equals negative 8 t minus 1.75 squared plus 4.5. Okay? And there you have it. So, the next one said solve this. Okay, solve it graphically. Well, it's kind of already solved for us. You can kind of see the solution here. But if we use Desmos, so we can get the exact value here. And let me just scroll ahead to our graphs. So plugging this into Desmos, let's turn these guys off. We now have negative 8, and I'm going to put t minus 0.75 all squared plus 4.5, and it looks like it doesn't like, I have to make this equal to 0, and I'm going to make this x instead of t. Okay, that's one, and the other one. So I mean, in Desmos, you're going to have to rewrite it in terms of x for it to actually graph it. There's probably a way to get around that, but let's not fight it. Okay, so there we have the two graphs exactly as it's shown. You zoom in to the point of intersection, and there it is, 1 and 4. Okay, that's what it's telling us. So the solution to the equation is 1 and 4. Which cannot possibly be correct, so I must have made a mistake. I'm so sorry. If you look at the intersection point, it can't be. Let's go take a look at our graphs here. Oh, that's because they're not equal to anything. Let's make this one equal to f of x. And let's make this g of x. And here's my mistake right here. This should be 7.5. There we go. Perfect. And now our intersection point comes to be 1.25 and 2.5. So we take a look at that. Right there. Okay. 1.25 and 2.5. Which when you look at this 1.25, completely makes sense. 2.5 looks completely correct, and so that is our solution. Okay, let me just turn this around. So we get, this is part A, so for part B, our solution is 1.25 and 2.5. We can verify that, that'll be correct, and what is happening here? Remember, we have one guy being flung into the air, right? Coming down, another person flung into the air. The point of intersection is basically when they will collide or high five or do some kind of flip or something when they meet. Okay? So, the time at which they meet is 1.25 seconds after the first one is launched. Okay, the height is 2.5 meters, I believe it was in meters, right? Yep. So that's how you interpret these results. Okay, so hopefully that made sense. Okay, sorry for the convoluted process at the end, but I'm working through these questions with you. Okay, I don't have them pre-prepared, so you can kind of see my thought process. And certainly check your work, right? I could see a lot of people just accepting the answer that this graphing calculator spit out, but if you gotta make sure it makes sense. Okay, so we made a little mistake there, but fixed it up, and now hopefully you should be able to move on to the practice problems. Once you're done that, move right on to section 8.1, 8.2, which is the last section actually in the chapter. Okay? So good luck with that.